Hi everyone, it's good to be here. I wish I could be with you in person. I miss everybody, and so much so that I often have a conference dream where we're together, and we're sharing meals, we're talking about math, trying to prove theorems. Today I'm going to talk about diagrammatic algebra. This is the first of two talks that I intend to give in this forum. It's based on joint work with Seiichi Kamada. Hi everyone, I'm Scott Carter. Wish I could be with you in person. Today I'm going to talk about diagrammatic algebra. This is based on joint work with Seiichi Kamada, with many thanks to Masahiko Saito. Seiichi and I have just finished a book yesterday. We're going through proofreading, and we hope to have it to the publisher in about 6 weeks. And the book is called Diagrammatic Algebra. The slides that you're going to see here are many different pages of the book. I'll try not to give them too much of a short shrift because the book's, 400 or more pages long, lots of pictures, virtually a picture on every page. The first part of this talk is going to talk about roughly chapter 6 and 7 of the book, and a little bit of some earlier chapters. It's about embedded surfaces in free space. So we're going to talk about surfaces, we're going to do some generalities on linear algebras, discuss Frobenius algebras for a short time, and then we're going to study a multi-category of something that has two objects, has arrows between the objects, and then arrows among the arrows, higher order arrows among the arrows. And one of the important questions will be, which objects do we want to consider? In part 2 of the talk that I'll give next time, we're going to talk about braid groups, braid charts. We'll also revisit the Frobenius algebras briefly and talk about their categorification. And then we'll have braid charts and braid movies, chart movies and curtains. So, and we'll also have curtain movies. Curtain movies are what we can use to construct braidings of 4 manifolds in 6 space. There are 5 categorical principles that formulate how we approach the subject. And the principles are that different things are not the same. They may be naturally isomorphic. Arrows in a category are used to compare things. And when an action or arrow is applied and the process is reversed, the result may or may not be the same as an action. So an arrow followed by its reverse can be compared by an arrow of larger degree to staying still. Colloquially, we say that doing followed by not doing may or may not be the same as undoing. Simultaneity is illusory. This leads to the idea of an exchange. Change followed by exchange is comparable to exchange followed by change by an arrow of higher degree. So let's review that. Different things are not equal. Arrows are a means of comparison. Doing followed by undoing is comparable to not doing. Simultaneity is illusory, and exchange followed by change is comparable to change followed by exchange. So I want to talk a little bit about abstract tensor notation, because the abstract tensor notation is what we use to formulate the categorical approach. So a vector x is written as a lollipop, maybe with a superscript, and maybe not. We can also think about x as an embedding of the real line of a line into the vector space, because once you have the vector x inside the vector space, then you can look at all the scalar multiples of the vector, and that set of scalar multiples forms a line. We can write a linear map. First we compute its action on the basis and write that as a linear combination of basis elements. So the coefficient of the basis element EI prime is the real number Aij, where j is the basis vector that we started with. And so this is a superscripted and a subscripted entity, and we'll take the superscripted and the subscripted entity and replace it by a box with a superscript or a subscript, or simply a box with a string that goes in from the bottom and emanates from the top. Associativity of matrix multiplication is expressed by stacking boxes on top of each other, or if you like, over on the right side of the slide, we can consider the composition of A and B and then compose that with C, or we can consider the composition of B and C and then compose that with A, and the associativity axiom says that those two compositions are equal. A inner product, or a bilinear form, is a function wedge, where wedge of a pair of linear combinations is computed as alpha 1 b1 times the value of the composition on the value of the inner product on the basis elements v1 and w1, alpha 1 beta 2 times the value of the inner product on the basis elements v1 and w2, alpha 2 beta 1 on the composition v2 v1 on the pair v2 v1, and alpha 2 beta 2 on the pair v2 w2. More generally, tensor is just a box with input lines and output lines. The standard inner product we can write as a cap, and it can be, the standard inner product is expressed by saying that cap ij. Now remember, cap ij is going to be the coefficient of the inner product applied to ei, comma ej, and so that's going to be a Kronecker delta at 1 if I is equal to j and 0 otherwise. And one can show that the standard inner product is non-degenerate in the sense that there is a coproduct, and the coproduct composed with the product in the sense depicted at the bottom, either on the left of the diagram or the right of the diagram, that those two compositions are the identity map. An algebra is a vector space with an associative unital bilinear product, and I will not spend a whole lot of time on this slide other than saying that when we compute the associativity map in terms of the structure constants, we get that the items on the left and the items on the right are equal, and that eventually we're just, because the WLs are basis elements, we're going to write that in terms of the structure constant. Over on the right of the slide, we have structure constants for the unit map, and the unit, the product applied to the unit is the same as just computing WL or WJ in either case. And, right, WJ or WI. Let's see if there's anything else that I want to say about this slide. Right, it's a pain, right? You have all these superscripts and subscripts, and it's just a pain to keep track of. What you're keeping track of is the structure constants in the algebra. What happens when you multiply a pair of basis elements? What's the coefficient in the third and another basis of those quantities? So associativity, when it's expressed in terms of the structure constant, has this equation involving the lambdas. In the lambdas, we sum over all p on either side of the equation, and we can think about summing over all p as sort of stringing one lambda on the top to one lambda on the bottom, and we can rewrite that. In fact, the equations are reversed, so the left-hand side of the equation with the structure constants is written on the right-hand side of the equation with the tree diagrams. And the unit axioms, so we have something that's a left unit and a right unit. And we want to play with the ideas of this algebra diagrammatically. So in general, a Frobenius algebra is a vector space for which there are bilinear maps, a multiplication, a pairing that's non-degenerate, and there's a unit. So the multiplication is supposed to be associative, the unit satisfies unit axioms, and the pairing is non-degenerate in the sense that there exists a co-pairing such that the zigzag composition of pairing and co-pairing is the identity in either direction. We also want the pairing to be an associative pairing. So in particular, on the right-hand side of the slide, we indicate why n by n matrices are a Frobenius algebra. And the idea is that the unit in n by n matrices, of course, is the identity matrix. That's a matrix that has ones along the diagonal. And so we can express that by means of a cap. The cap is a map from the ground field into the vector space, and that into the space of matrices, and that cap then captures the fact that one goes to the diagonal matrix. The co-pairing is defined as the trace of the product of two matrices, and so in order to multiply the matrices over on the bottom, we can consider what happens when we multiply basis elements. So the basis in the middle, Ej, is multiplied by Ek by a standard matrix product. Ei is multiplied on the outside of that, and L is multiplied on the right side of that, and so we get that matrix product delta Pi, delta Jk, delta Ql is what happens when you multiply the basis matrices for the matrix algebra. The basis matrices are the outer products of the column vector, the ith column vector together with a jth row vector, and so that's a matrix with zeros everywhere except in the ijth entry. So you need to know how to multiply such a matrix with another matrix that has a whole bunch of zeros and a single one. And there you have it. That it is a Frobenius algebra just follows because we're going to be able to manipulate the caps and the cups according to these slides, and everything works out. It works out nicely. It works out nicely because we believe that we're working with structure constants, and so they have nice commutativity properties, but it also works out nicely because the diagrams do work out nicely. And so in fact, there's something more to the Frobenius algebra. There's this underlying category, which is the category of diagrams subject to these conditions. And on the second lecture, we'll try to relax these conditions that we've written as equality and relax them to only being isomorphisms. So we'll have in a multi-category that we're going to consider, we're going to have schematics for the identity map. The identity map is just straight strings that are going up. We can have alpha strings and beta strings, and so we can combine those to alpha plus beta strings. And we can have alpha plus beta strings and split those, or we could split them as indicated on the right of that. These diagrams should be considered to be analogs of jumper cables that used to be in the back of the computers. I haven't opened up a computer in a long time. They're just straight strings that are running through the ribbons, and the ribbons really don't matter. In the Frobenius algebra, we also want to have arrows, which are unit, co-unit, multiplication, co-multiplication, pairing, co-pairing, and identity. And if A and B are arrows with suitable sources and targets, then we can compose A over B. We can take a tensor product of A with an identity either on the left or right, and we can express the identities as in expressions 4 and 5. So those are all arrows, and then the composition of arrows can be rescaled, and everything here can, in the next row, can be interpreted as an identity, and so that's how we form arrows. We have an exchanger axiom, so if we have an arrow F from alpha to gamma, and we have an arrow G from beta to zeta, then there's a natural family of isomorphisms. You see over in the middle left of the picture we have F over G or G over F, and by the maxim that simultaneity is illusory, then we're not going to allow those F's and G's to be at the same level. They can be at different levels, and we can compare them by means of an exchanger. The exchanger is expressed algebraically on the upper left side of this slide, and then it's expressed diagrammatically in a couple of forms. So we exchange the heights of F and G, and when we exchange the heights of F and G, we consider that black box G and the black box X to exchange one in front of the other. There's an inverse exchanger, and the exchanger satisfies a naturality axiom. One expression of the naturality axiom for the exchanger is the Rademacher type 3 move. Another expression of the naturality of the exchanger is, as in the upper left of the right-hand slide, that change followed by exchange is the same thing as exchange followed by change. So here change is represented by the box with the script R, and there are various manifestations of that exchanger within that slide. Okay, so we'll take the category one step further, and in that context, equalities are replaced with higher order arrows. For the rest of today, we're going to abstract a related idea. So I want to have a multi-category. It has two objects. They're called from and to, F and T, and we're going to have generating arrows P from F to T and B from T to F. So if you think as moving from to to, then that's positive, and it's bad if you move to from. There are also identity arrows, because we have to have a category, so we have to have identity arrows on F and identity arrows on T. And we're going to say that P and F are reverses of each other. And so a non-identity arrow in this category is just a sequence of raspberries, either PB, PB, blah, blah, blah. B could be end in P, could start with B, end in B, start with B, and end in P. And those expressions, instances of identities arrows, are always been contracted. Juxtaposition is used to compose one arrows. Now, so we have the objects T and F. One arrow is generated by B and P. In general, one arrow is a finite sequence. And then we have two arrows. You see, if we start at F and move to T by means of P, and then move back to T by means of B, then we can compare that composition by means of a double arrow upside down F, which compares that with the identity on F. Or, and there's an upside down arrow F, there's a upside down arrow F of T, there's a right side up arrow F of T, and there's an right side up arrow F of F. So those are how we compare the various compositions of either P and B with the identity on F or with the identity on T. We also have double arrows, which are the identity on the identity on T, the identity on the identity of F, and the identity on B and the identity on P. And now let's see how we can compose these things. So we can depict this double arrow as anytime we need to, we can always expand a given object by means of an identity arrow. So we can depict the arrow f of t in this box form, and we can compose we can compose these arrows in different ways. So on the left-hand side, we have two different skew compositions of F and upside down F, and on the right-hand side, we have direct or globular compositions. So we can compose F of t with its reverse, capital F of t with its reverse, along the identity on T, or we can compose it with a reverse along the composition BP. So this is how these arrows can be put together. They can be put together by skew compositions on the left or globular compositions on the right. Now, we can now consider triple arrows. So if we take the globular composition at the bottom left of the movie, that globular composition is composed along BP, and you see the source of that composition is the identity on T. The target is the identity on T. And so we should be able to compare that composition to the identity on T. And one comparison would be going from the globular composition to the identity, and that would be called a positive death. The other composition is going in the other direction, and that's called a positive birth. There's a negative death. Most deaths are negative. And that's going to be a comparison with the globular composition with the identity on F. And then there's a negative birth, where we start with the identity on the identity on F and compare that with a globular composition along the path PB. So those are some of the triple arrows we have. We also have triple arrows which are a positive fork and a positive saddle, a negative fork and a negative saddle. So for terminology's sake, a tailor, when adjusting the pants, will ask how it fits in the fork. And so the fork of the pants is where the legs converge. And so here we take the other globular composition of F of t and upside down F of t, or F of F and upside down F of F. And so those are all going to be forks or saddles. And we need to make a distinction between forks and saddles in these contexts. Okay, so we have also skew compositions of F and upside down F, and we can compare the skew composition with certain identities, either with the identity on P, either as on the left, top left, or on the top, I guess it would be entry 1, 2 on the top. And those are called positive right cusps. Below that, on the left of the figure, we have, what do we have? We have negative right cusp. And on the other side, we have a positive left cusp, up and down, or down and up, where the vertex of the cusp is where we give the direction to the cusp. And that completes all the twofold compositions of these arrows. And whenever we compose those two arrows, they're always comparable to certain identity arrows. And that's where the triple arrows are coming from. they're either birth, death, saddle, fork, or cusps. And so let's recap everything and start talking about quadruple arrows. So we have two objects, F and T. We have generating arrows P and B, and these are reverses or weak inverses of each other. The objects F and T are identity arrows upon them, and the arrows P and B generate a category. Since the arrows P and B are weak inverses, there are reverse pairs of generating double arrows, these various Fs, and these are pairwise weak inverses. The one arrows and the double arrows form what's known as a sesquicategory. Double arrows can be composed globularly and in a skew fashion, but horizontal composition are mitigated by a natural family of triple arrow exchangers. We haven't gotten to the exchangers much yet. Since the generating double arrows appear as weak inverse pairs, there are triple arrows of the form plus or minus birth, plus or minus death, plus or minus saddle, plus or minus fork. And then you have the 8 cusp-like triple arrows that were listed in the previous slide. And triple arrows are going to be composable in globular and skew fashions. And then we're going to describe quadruple arrows. I guess I should back up a little bit and talk a little bit about triple arrows. And so I'd like to consider a geographic metaphor. So if we consider the southern hemisphere of the globe, and along the equator we pick 2 points. Let's say one point is below the coast of Equatorial Guinea, and the other point is antipodal to that. I forgot what island is antipodal to that. And then we have arrows running along the eastern hemisphere along the equator. One of them will pass through the Galapagos. And then we have another arrow that runs along the western hemisphere. And these both point to the object just below the coast of Equatorial Guinea and away from the coast near the point near the international date line. So those are 1 arrows. They're objects as points. The 2 arrows are the southern hemisphere, and then we can consider a slice through the sphere as another 2 arrows. So we can then consider the southern hemisphere of the Earth, the solid portion of that, as a triple arrow, and then compose that with a triple arrow in the northern hemisphere. It's as if 2 pierogies or 2 dumplings are stuck together along part of their skin. The quadruple arrows that we want to have are critical cancellations. So a birth cancels with a fork, either positively or negatively. A saddle cancels with a death, either positively or negatively. And so we have on the left-hand side of the slide, we have the positive birth canceling with a positive fork, or a positive saddle canceling with a negative death. That's easy to remember. Death in the saddle, birth at the fork. Okay, so we have an example movie move of this phenomenon. And actually, this movie move describes 2 of those processes. So let's look at the middle left of this slide. In the middle left of this slide, we have this circle together with a arc above it. Now we could envision that that was caused by means of a birth, and then the arc, the semicircular arcs are canceled by means of a fork at the top of the picture. Or, and this is kind of cool, we could start with the middle picture and consider that it was formed from the bottom picture by actually passing through, let's see, a saddle. and then the circle is annihilated by means of a death. We'll see some other pictures of this later where that'll become a little bit more clear. At any rate, the source and target double arrows of the movie on the left are the same, and so this entire process can be compared with the identity on the map upside down F of F. So that's an example movie move for the cancellation, for the critical cancellation. We have ellipse cancellations. These are what happens when cusps cancel, and this movie move on the right exemplifies one of these ellipse cancellations. We have beak-to-beak cancellations, and so the movie move on the left is an example of one of these cancellations. They're left, right, positive, and negative beak-to-beak moves. And we have horizontal cusps. Generally speaking, I like to spend a lot of time on horizontal cusps. I will spend more time on horizontal cusps in some other examples, but I'm not going to be able to do so now. So we just want to say that these slides exist. This is an incredibly nice equation if you think about it as the composition of a cup with a wedge is equal to a cap with a V. And in fact, you can get all these horizontal cusps by means of that single expression. This is an example movie move of the horizontal cusps. So on the left-hand side of the movie move, to get from the bottom still to the next still, we perform a saddle move. To get to the top still, we perform a cusp. On the bottom, we perform a cusp, stretching that arc on the right to twist above, and then we perform a cusp to get to the top picture. For swallowtails, there are 4 types of swallowtails here, and here is an example movie move of the swallowtails. I'm sorry, there are actually 8 types of swallowtails. It's just that they're mutually comparable to identities. The naturality of the exchanger in this context is always expressed like this, and the reason is that there are never any arcs emanating out of a birth or a death or a cusp. So that's how naturality looks for the exchanger. And I hope that the previous terminology helps you see why they are births, deaths, forks, and cusps. So in fact, if we have a properly embedded surface, we can project that surface to the plane generically, and we see all of these critical phenomena. We have exchangers expressed, we have forks, cusps, births, etc. And the theorem, which is a classical theorem, is that a generic, properly and smoothly embedded surface in R2 times I, where the boundary can be decomposed into a positive and negative piece, it corresponds to a globular composition of homogeneous triple arrows in this category, multi-category that we've described, and properly isotopic surfaces correspond to equivalent homogeneous triple arrows. By equivalent homogeneous triple arrows, we mean triple arrows that are related by the quadruple arrows that we just expressed. And given such a globular composition, you could represent it by means of proper embedded surface. And that's classical. It's been known for more than 20 years. It's part of the Tangle hypothesis. And so let's see just a little bit of this in the surface case. And so I'm going to, on the illustration that we saw before, I'm encircling that with a blue circle. And the movie on the left-hand side is an expression of what happens in that blue circle. So to go from the bottom still to the next still, there's a fork, then there's a cusp, and then there's a second cusp, and then the maximum of one of the cusps is canceled with the minimum of the other by means of a fork. And then we simply express everything in terms of f's on the right-hand side of that movie. And then also on the right, we've indicated what the triple arrows are that connect various stills. Of course, if we interconnected those stills by means and included identity arrows, we'd have exactly the encircled part of the picture on the left, on the right, excuse me. Okay, so why these particular 3 and 4 arrows? The reason is, well, let's just consider one of the f's. So we're going to consider capital F of t. This is from the composition BP to the identity on t. And then just figure out all the different ways that we can compose that. So we can either compose it with an upside down F of t on top of it. We can compose it globularly as in the left-hand disk, or we can form these 2 skew compositions on the bottom right of the left-hand slide. We can also form the threefold compositions. So these are all the threefold compositions that we can form that involve F of t. And in the middle, because simultaneity is illusory, then we have to tilt that thing up. So we tilt that up, and that tilting process, by the way, involves a choice, and that's the change in the exchanger is the exchanger in the swallowtail picture. Okay, so now we're going to go beyond surfaces and ask, well, what are T and F? You see, we didn't say what T and F were, so in the first column we could let F be empty and let T be a dot. And then P is like a unit and B is like a co-unit. We could have let F be 2 dots, 1 dot, and T be 2 dots, and then P is a Y and B is a lambda. Or we could go from 2 dots to no dots, and P is a cap and B is a cup. Or we could go from a circle to nothing, and then P is a death and B is a birth. Or we can go from a pair of arcs to a cup cap, and then P and B's are saddles and forks. Or we could go from a sphere to nothing. Or we can go from a cylinder to a yarmulke and a bowl, or other things. So in this multi-category S that we've described, we can start looking at what the higher order arrows are. And we're going to do a little bit of that here and now. So for example, in the Y lambda case, then it's not real easy to see in this picture, but on the upper left we have a bit of bubble wrap and we pop the bubble, or we have a bit of cardboard and it bubbles out, and those are the negative deaths and births. In this context, the positive births and deaths are where you have 2 sheets stuck together. You can rip them apart, or you can glue them together along a disc. The saddles and forks are identities among these foams, and the horizontal cusps are illustrated on the right-hand side. I'm sorry, those are critical cancellations, are illustrated on the upper right-hand side, and one of the horizontal cusps is illustrated in the bottom middle right, bottom middle. Okay, so that's nice. In case we have, I guess this is the case where we have straight strings as one thing and cup cap is the other. Then we have different types of births and deaths, and these events correspond to handles. Cusps correspond to handle cancellations, and horizontal cusps correspond to rewriting handle cancellation rules. Okay. This is a nice, complicated slide, and we've been going for a long time, and I'm certainly glad that we can pause these things and you can think about them more carefully. But let's think about the case when we have an empty object or a circle, and then the identity on the empty object is just an empty frame. The birth of the circle is the birth of a circle. A birth followed by a death is a sphere, and that birth followed by a death sphere is comparable to nothing, and that comparison is the birth of a sphere. Or correspondingly, the sphere can die. So the composition of those things, sphere born, sphere dying, is simply a three-sphere, and that composition is comparable to a four-dimensional zero handle, or is comparable to nothing, and that comparison is a four-dimensional zero handle or a four-dimensional four handle. In the case that we do compare PB, so the composition PB is a yarmulke or skull cap below a bowl, and that's comparable to a cylinder. And that comparison is a two handle or a one handle, depending on which direction you're considering it. On the right hand side, we have other comparisons. So we compare a sphere death to a sphere, and the composition of a sphere death followed by a sphere birth to the identity on a sphere, and those are either four-dimensional three handles or one handles. And I don't think I want to describe the rest of the slides. I'll let you look at them and consider how they work. So if you read along the horizontal row, that should be a still in one of the movies, and then the comparison between one side of the movie and the other side of the movie is a comparison to an identity object, or an identity arrow of the appropriate size. And I'm lost about which size arrows we have, although I'm pretty sure that all of the two handles are labeled correctly. The cusps are critical cancellations, and the swallowtails are interesting rewritings of things. So for example, in the upper right, a sphere is born, another sphere is born above that, and then they're surgered together by means of a one handle, or a different sphere is born, a sphere is born below that, and they're surgered together by means of a different handle. And that's ultimately either is comparable to the birth of a sphere. So these are swallowtail relations. The cusp cancellations are also indicated if you read carefully. Horizontal cusps in this scenario are shown here, and I did say that I'd say more about horizontal cusps. So you see that on the bottom left we go cap followed by birth followed by death is this sphere above a skull cap, and then that's morphs into a bullet, and the bullet is corresponds to a cylinder topped off by a cap. And then on the horizontal cusp, you see you can just interconnect each level by certain things, and I think it's better to contemplate those, so you should just pause this and then when you're ready to continue, you can continue. We had other versions of these. These all correspond to different types of handles in different contexts, and cusps correspond to different handle cancellations, and horizontal cusps correspond to different reparameterizations of handle cancellations. And I do invite you to stop the still, maybe get a screen capture of it and blow it up so you can see all the details here. This bit is really amazing. It's really nice how nicely it works. It works nicely because we can do things inductively. So we're going to use some variation of binary notation here. So identity K arrows will be either labeled by F with a binary subscript, or so identity K arrows are going to be labeled by F with a binary subscript, and we're going to let P and B go from F's to T's, and so F is the identity 1 arrow on 0, and F1 is the identity 1 arrow on 1, then T0 is going to be the composition PB, and T1 is going to be the composition PB. And that means that each epsilon here, it lies in 0, 1. So we have a binary sequence x epsilon k through epsilon 1, and we have objects tx and fx, and then we create 1 arrows from them, and we inductively define f's and t's. F's are identities, t's are arrows, and then the generating 2 arrows, or the generating arrows at the next level, are going to be comparisons with compositions of PBs. So you either compare with a PX, BX, or you compare with a BX, PX, and you can do those comparisons in either of those 2 ways. And you have over on the right hand slide, F is an identity if the first subscript is a 0, it's the identity on f of x, and if the second subscript, or the first subscript is a 1, then it's an identity on t. The t0x is px bx, and the t1x is bx px, and then you define those generating arrows of higher order as p's and b's of higher order, and this is what the situation looks like. So you just do this, okay? So on the left-hand side of these slides, you have birth and death arrows, or settle and fork arrows, and then you sort of break those down, compress those into being arrows of smaller dimension on the right-hand side of the stills, and then you have cuspal arrows, and cancellations are indeed, critical cancellations are indeed cuspal arrows. And what else do I want to say about this? So we start out with arrows as objects. We take 2 arrows to be 1 arrows, and then we take 3 arrows to be 2 arrows. Just starting from nothing moving to something is to essentially it's a way of passing through surface. So it's a way of passing through the door to get out of here. And we will be getting out of here shortly. We have 3 arrows, and over on the right hand side I've indicated Yeah, up to level 8. So we have births, P's and B's for 0, 0, 0, 0, 0, 1, and so forth. Yeah, there are 8 of those. They're the other 4. They're the other ones are indicated there. And then there's 16 of those at the end. And yeah, so just starting considering what you can do with a cancellation, these original capital F of F's and upside down F's of F's, then all of a sudden you get handle theory. And I think that's a really nice story, and I hope that you enjoyed it. I'll see you next time.